A couple of days ago, we used the wire grasp rule to find the direction of the magnetic field caused by a moving charge. If you remember, it was 200 years ago this year that Hans Christian Ørsted discovered if you have a moving charge, it generates a magnetic field. The wire grasp rule tells us that if we have a negative particle represented by this X, the magnetic field that surrounds this moving particle into the page would be counterclockwise. This isn't new. This moving charge particle generates a magnetic field that's counterclockwise. 2 days ago, you could have answered that question. But what if this negatively charged particle moving into the page, producing its own magnetic field, happens to be moving through what we call an external magnetic field? A magnetic field that was already there. So it generates its own magnetic field. We'll call that B1, the magnetic field that it generates. But it goes through a magnetic field that's already there. We'll call that B2. That magnetic field B2 could be caused by maybe the Earth's magnetic field. Maybe it's a magnetic field caused by bar magnets. Whatever it's caused by, it's already there and it's not caused by the moving charge. What happens then? Well, if I have two magnets, they both generate magnetic fields, and they will interact with each other to produce a force of attraction or a force of repulsion, depending upon the polarity. When you have two magnetic fields, they will interact with each other to produce a magnetic force. Now, the magnetic force produced here is a little bit tricky. It's not as simple as saying, oh, here's a north pole, here's a south pole, they attract, or here's a north, they're going to repel each other. We're going to have to use another hand rule to determine the direction of the magnetic force here. And we're going to call that other hand rule the hand rule for deflection. So that's the third of the three rules. The hand rule, the wire grasp rule, the coil rule, and now the hand rule for deflection. It's used to find the direction of the magnetic force. This is the only hand rule that involves magnetic force, right? Remember the wire grasp rule, magnetic field caused by the moving charge. The coil rule, the magnetic field caused by the coil. The deflection rule, the magnetic force on a particle that's moving through a magnetic field. Now, notice that I also have the word perpendicular there. We talked about that a little while ago, right? We're going to see that many, many times through this unit and through the next unit. The rule that I'm about to teach you works if and only if the charged particle is moving perpendicular to the field. So if the charged particle is moving to the east and the magnetic field is to the north, all right, they're perpendicular. Good, this rule works. If the charged particle is moving to the east and the magnetic field is downward, they're perpendicular. The rule works. If the magnetic field is to the east and the charged particle is moving to the west, they're parallel, and this hand rule doesn't work. We'll deal with that in just a few moments here, what to do if that's the situation. If they're parallel, however, this rule works. This rule has three variables. Unlike the other two rules, which have just the thumb and the bent fingers, this rule has thumb and straight fingers. Remember I said in the last two rules, you bend your fingers a little bit, a lot, doesn't really matter how much you bend them. This one, it does. This one, you can't bend them at all. They got to be straight. Thumb, fingers, 90 degrees to each other, fingers are going to be straight. Now you also have a third variable in here, and that's the palm of your hand. So how does this work? You're going to stick your thumb in the direction of the moving charge or in the direction of the electric current. And it's going to be your left thumb if it's a negative particle. It's going to be your right thumb if it's a positive particle. Whatever way the particle is going, stick your thumb. Your straight fingers, now pay attention to this, your straight fingers are in the direction of the external magnetic field. So there is a magnetic field that's caused by the moving charge, and there's an external magnetic field, the one that was already there. That's the one we're talking about now, the one that was already there. Your palm will automatically point in the direction of the magnetic force. Now, sometimes Most times, you're given the direction of the moving charge and the direction of the field, and you need to find the direction of the force. But sometimes you got to rearrange it. You're given the direction of the charged particle, you're given the direction of the force, and you have to see which way the field points. It's not a big deal. You know you have thumb, fingers, palm, like this. If you're given thumb, fingers, just see which way your palm points. If you're given thumb, palm, let's just see which way our fingers point. If we're giving fingers, palm, let's just see which way my thumb points. Okay, as long as you keep your hand like this, straight fingers, the fingers 90 degrees to the thumb, should work out no matter what variable it is that you're looking for. Let's do a couple quick examples, and then we'll give you a break for a minute here. Let's say we've got a magnetic field that's pointing this way. Let's say we've got a charged particle. Let's make it a negatively charged particle that's moving this way, down the page. Hey, are those perpendicular to each other? Yes, they are. That means the rule that we just learned works. This is a negative particle, so we're going to use which hand, left hand or right hand? Left hand, yeah, left hand. So let's say thumb, left thumb in the direction of the particle. My fingers are going to point in the direction of the external field. There is a field that's caused by this moving charge. I don't care what it is right now. I'm going to just put my fingers in the direction of the external magnetic field, which is to the right. My palm's going to point which way? Towards the page, towards the page. I'm going to say the force, which is going to be represented by red here, is into the page. Let's do another one. Let's say this time my magnetic field is into the page. I've got a charged particle that's moving to the right. Are those perpendicular? Into the page and to the right. Are they perpendicular? Yes, look. That's into the page. Okay? This is to the right. That's 90 degrees to each other. That's perpendicular. So I'm allowed to use this hand rule. Let's do it. Thumb in the direction of the particle, straight fingers in the direction of the field, which is into the page. Which way is my force? Which way is my palm pointing? Yeah, down the page. Don't say down, say down the page or toward the bottom of the page. Do you see that? We don't want to say down. Here's why. Like you do this according to my page up here. My page is vertical, right? Your page is horizontal. You do it on my page, down the page is down, right? But if you do it on your page, look what happens. Thumb, fingers, it's towards the back of the room. Depends on which way you have your page oriented, whether it's down or towards the back of the room or whatever. But if we say it's toward the bottom of the page, it doesn't matter whether we have our page like this or like this. It's still toward the bottom of the page. So when our frame of reference is the page, we're just going to express our answer always relative to the page. I'll say down the page, or you could say towards the bottom of the page. Let's do another one. Let's say this time we've got a charged particle that's moving, charged particle moving into the board, into the page. We've got a magnetic field that's pointing, an external magnetic field that's pointing this way. Hey, are they perpendicular? Charged particle is going this way, magnetic field is this way. Are they perpendicular? Yes. Does this rule work? Yes. Okay, then let's do it. Thumb in the direction of the particle, which is into the page. My fingers, which are straight this time. Thumb points into the page. Fingers point down the page. Palm points to the right side of the page. Good. Not to the right side of the page. Excellent. How about this one? We have a charged particle that's going to the north. North, by north I mean like what we typically think of as north, magnetic south. Okay, the Canadian Arctic, north. Okay. So a charged particle moving to the north. Actually, let's change that around. We have a charged particle that's going to the west. we have a magnetic field that's going to the north, which is magnetic south, which is the way the Earth's magnetic field points, right? Which way is the direction of the force now? Charged particle going to the north. Which way is north? Which way is north? In this room, which way is north? That way, correct. What happens if on diploma exam day you get put in the cafeteria or you get put in the gymnasium and you kind of get turned around and you're like, I don't know which way is north. I can't do this. What should you do? Make it up. Make it up. It doesn't matter which way is north. All you got to remember is that south is opposite north, and that east is to the right of north. I don't know about you guys, but I can picture a map of Canada. You might not get every provincial capital right or whatever. Doesn't matter. Okay, I know that British Columbia is on the west coast, and I know that Nova Scotia, New Brunswick, and Prince Edward Island are on the east coast. So I know my north, south, east, and west. Okay, if I've got a problem where my magnetic field is pointing to the north, and I've got a charged particle moving to the west, and I don't know which way north is, I guess. Let's guess that that's north. Okay, that way is north. It's not really, right? But let's pretend that it is. Because you're in this room, in this cafeteria, you're turned around, you don't know which way is which. Pretend that that's north. If that's north, and we've got a particle going to the west, all we got to know is west is to the left of north, right? So if that's north, then that's west. Got it? We have a magnetic field pointing to the north. We have a charged particle pointing to the west. So thumb to the west, fingers to the north, palm points which way? Dylan, which way is it? Up. We don't have to say up the page this time. Our frame of reference is the Earth. It's just up. So in that question that I just gave you, charged particle going to the west, magnetic field going to the north, the magnetic force would be, in that case, just up. Some people might say out of the Earth. Yeah, that's fine, out of the Earth. But what's out of the Earth? What's another name for out of the Earth? Up. Right? Does that make sense? All right, so we know how to find the direction of the magnetic force. Let's see how we can find the magnitude of the magnetic force. In other words, how strong the magnetic force is, the strength of the magnetic force. We can find the magnitude of the magnetic force by a relatively simple equation. We're just going to say Fm. Notice the absolute value signs are on it. In other words, the equation I'm about to tell you does not provide for us the direction. That's okay. We know how to find the direction, right? We're going to use the hand rule for deflection. The magnitude of the magnetic force is equal to Q. That's the strength of the charge. Makes sense, right? The stronger the charge is going to be, the higher the charge is going to be, the stronger the magnetic force is on that charge is going to be, times V, the speed of the particle. The faster the particle moves, the stronger the magnetic field it generates, and the stronger the magnetic field it generates, the stronger the magnetic force is going to be. And finally, the last variable is B. B stands for the external magnetic field. The magnetic field that was already there. Of course, the stronger the external magnetic field is, then the bigger the force is going to be. So B is the external magnetic field, V is the speed of the particle. That's going to be measured in meters per second, and Q is going to be the charge of the particle. Now there's one more thing that I want to add in here, and that's a little upside down T after the V. A little upside down T. What do you think that means? Perpendicular. You got it, perpendicular. In other words, this equation is only valid when the charged particle is moving perpendicular to the magnetic field. Same as the hand rule for deflection is, right? Everything we've learned here so far today is only valid when the charged particle is moving perpendicular to the field. Now, I'm going to write down something on the side here. You don't need to write this down. I just want to show you something with this. This equation is actually a simplification of the actual equation, but this is the form that we'll use in Physics 30. If you go on in physics, you're going to learn an equation for magnetic force. It's equal to Q times V cross B. Not times B, it's cross. It's called a cross product. That turns into another equation that looks like this. F is equal to QVB sine theta. This is the actual equation that we, well, that personally that I think we should be using, but we don't go into this much detail in Physics 30. Theta stands for the angle between V and B. It doesn't have to be perpendicular if we use this equation. Now, if I make it 90 degrees perpendicular like this, what does the equation become? What's sine 90? 1. So the equation becomes QVB, right? So if they're perpendicular, then the equation becomes QVB. Agree? What if they're parallel? Theta is either going to be 0 or 180 if they're parallel. What's sine 0 or sine 180? What is it doing? 0. Okay, so if the particle is moving parallel to the field, then the equation for force is Q times V times B times 0. In other words, if they're perpendicular, then the equation that we just learned and the hand rule for deflection work. If they're parallel, they don't work, but that's okay because there is no force. If the charged particle is going to the north and the magnetic field is to the north, what's the force? 0. We don't have to worry about an equation or about a hand rule because there is no force. Now, if it's something in between 0 and 90 degrees, that's another story altogether, but we don't have to worry about that in Physics 30. That's for another year of physics. Got it? Perpendicular, use what we learned here today. Parallel, force is 0. In an ideal world, everything's parallel and we don't have to do anything because the force is 0. Let's do one example, and then we'll set you free on a few questions on your worksheet, okay? Example number 1 says a proton is traveling at a speed of 5 times 10 to the 5 into the page through a magnetic field that's to the right of the page. Hey, are those into the page, to the right of the page, are they perpendicular? Yes, they are. So in other words, the equation that we learned, the hand rule that we learned, they're valid, right? Like you're reading through this, you're kind of hoping that they're going to be parallel, right? Because then the force is 0 and we don't have to do anything. But if they're not parallel, at least it's second best here. They're perpendicular, and what we learned about works here. We're going to find the magnitude of that force by saying F is equal to QVB. Really, it's QVB sine theta, but perpendicular, so 90 degrees, and it becomes just QVB. Charge of a proton on our data sheet is 1.60 times 10 to the minus 19 coulombs. The speed is 5 times 10 to the 5 meters per second. And the magnetic field strength is 2 times 10 to the negative 2 Tesla. It gives us a magnetic force of 1.60 times 10 to the negative 15 newtons. That's the magnitude of the force. What about the direction? How about the direction, huh? Up the page, toward the top of the page. Let's figure this out. Charged particle is going into the page, and it's a proton, so that's a right-hand deflection rule. Charged particles going into the page, thumb into the page. Fingers go to the right of the page. Palm points which way? Down the page, right? Use, oh, did you? Okay. Yeah, use your left hand. Yeah. So you did it right. I'm just looking at the way you've got your hand. You did it right. You just used the wrong hand to do it. So thumb into the page, fingers to the right of the page, palm's going to point down the page. Is that good? Not too bad, hey? I'd like you to take a look now at worksheet number 11. And I'd like you to do the first 9 questions on worksheet number 11. Now, I know that sounds like a lot. It's not really that bad. The first 8 questions are just hand rule questions, so they go pretty quickly for us. And the 9th question is a math question. So see what you can do on those 9 questions. You should be able to get a pretty good chunk of those done within the next 10 minutes. Then we'll take a peek at them, and then we'll do one more example, and then we'll call it a day. Number 1 says an electron travels to the right of the page. It's an electron, it's a left hand, thumb to the right of the page. Magnetic field is going into the page. You can see my fingers going into the page here. Which way is my palm point, Christian? Down the page, yeah. Toward the bottom of the page, or you could say down the page. We don't want to just say down, because if my page is turned horizontal or at an angle or something, then that completely changes everything, right? But anyway my page is turned, it's still going to be toward the bottom of the page. Take a look at number 2. An electron travels into the page. Okay, left thumb into the page. Magnetic field is pointing to the left of the page, all right? So thumb into the page, magnetic field to the left of the page. Where's my palm point? Where's my palm point? Down the page, yeah. Toward the bottom of the page again. 3, an alpha particle, this is a positive particle, so it's going to be a right-hand rule, travels toward the top of the page. Okay, right thumb toward the top of the page. Magnetic field points out of the page. Which way does my fingers, sorry, which way does my palm point? Towards the right side of the page. 4, an alpha particle, again, that's going to be a right-hand rule. An alpha particle travels towards the north. Okay, interesting. North, this is, the page is no frame of reference here. The alpha particle goes to the north, magnetic field goes to the west. Which way is the force? I don't know which way is north. Let's guess this way. So the alpha particle is going to the north, this way. The magnetic field points to the west. Well, if that's north, then that's going to be west, right? To the left of north is west. So I'm going to say thumb to the north, fingers to the west. Which way is my palm point? Up. We're not going to say up the page this time. Okay, you got it right. We're just going to say up because our frame of reference is the earth, not our page. So we're just going to say up. Or somebody might say out of the earth, away from the earth. But that just means up. An electron travels north through a magnetic field that travels north. Which way is the force? Zach? There is no force. Yeah, if the particle's going parallel to the field, there is no force, right? 6 is the same thing. An alpha particle travels out of the page. Magnetic field is into the page. They're parallel as well, 180 degrees to each other. The magnetic force is 0 in that case as well. 7, an electron traveling east, magnetic force to the north. Careful here. We've got thumb and palm this time. Thumb and palm, not thumb and fingers. We're guessing this is north again. The electron is traveling to the east, all right. If that's north, then that's going to be east. So I'm going to say the particle is traveling that way to the east. The magnetic force is to the north, so my palm points towards the north. My fingers point up. Yeah, so the magnetic field is going to be upward. This time we're finding the direction of my fingers rather than my palm. Alpha particle, this is right-hand rule again. It's traveling into the page. Magnetic force is to the right of the page. So my right thumb points into the page. My palm points to the right of the page. Thumb, palm to the right. Fingers point which way? Up the page. Good. Toward the top of the page or up the page. Do you understand the difference between 7 and 8? Where we have up versus up the page? When we got a north or a south or an east or a west mentioned, we're talking about the earth. There's no up the page here, it's just up. When we're talking about an into the page or out of the page, then we've got to make our frame of reference the page, and it's going to be up the page, down the page, whatever. Okay, number 9, this is a pretty straightforward question. We're just going to say for this one to find the magnetic force, F is equal to QVB. Charged particle is moving perpendicular to the field. We don't know which way that is, into the page or right or whatever, it doesn't matter, it's perpendicular. We can find the magnitude of that force by just multiplying those 3 numbers together. And when we do, we get 3.20 times 10 to the negative 12. 3.20 times 10 to the negative 12. Good? Okay, I have one more example, and then I'm going to shut it down for the day here. Second question says, 5 times 10 to the negative 25 kilogram particle with a charge of plus 1e. What does that mean, plus 1e? You guys remember that from our last unit? What's the e mean? Yeah, it's the elementary charge. 1 times the elementary charge. It's traveling out of the page. By the way, this is a positive particle, so if I'm going to use a hand rule, it's going to be a right-hand rule. Traveling out of the page, magnetic field is to the right. Those perpendicular? Yep. So the hand rule works, the equation works, right? Determine the speed that the particle must be traveling near the Earth's surface in order to not be deflected. If it's not deflected, what do you know about this situation? I could ask my Physics 20 class this same question, because we're just studying this kind of stuff, not magnetic forces, but forces. They would know the answer to this. I said, if it's not being deflected up or down, then it's in a state of, starts with an E, equilibrium. That must mean that forces must, starts with cancel or balance. Either you can use either one of those, right? Okay, if there's forces that are balancing or canceling, one of them is a magnetic force. What's the other one? Yeah, which one is it? Gravity. So gravity acts down, the magnetic force must act up, right? And they've got to balance each other if it's not being deflected. So we're going to say Fm, that's the upward force, is equal to Fg, that's the downward force. Now technically, they're not equal because one's positive, one's negative, but the magnitudes are equal. We're going to say QVB is equal to m times g, and we're going to rearrange this to solve for v. We get mg over q times b. The mass of the particle is 5 times 10 to the negative 25 times 9.81. The charge here is 1.6 times 10 to the minus 19. It's positive, but even if it was negative, we'd drop the negative. Times the magnetic field. Oh, I forgot to give you the magnetic field. We realized this morning that that there was a missing given there. The magnetic field was supposed to be 6.00 times 10 to the negative 5 Tesla. That was supposed to be given to you. We do the math on that one, and it works out to be 0.511 meters per second. So how fast does this really, really light particle need to be traveling in order to not be deflected? 0.511 meters per second. If it's going faster, the magnetic force ends up being too big and it deflects upward. If it's going slower, the magnetic force is too small and it ends up getting deflected outward. Your homework for tonight is to finish worksheet number 11. There's 3 questions on the back of that page that you haven't done yet. Okay, they're not crazy hard, shouldn't take you all that long. Please finish those tonight.